Okay, so today we're going to cover KP according to the Wjec A level spec. Now this is different to KC, but it's called the pressure constant, and it has a P in it. So it's all to do with pressure. Now the equation, which we looked at for KC, is very similar to this one. There's a few subtle little differences. So in this case, KP is equal to, it's still products of reactions, but we shove a little P in front of it. So it's P squared NH3, not 2, because it's still products of reactants, and P squared, because it's the stoichiometry, is 2. And this is over P of N2 times P cubed NH2. There you go. It's the same thing. Now, in terms of units, we still work out the same way. So they could tell you, oh, we're doing it in atmospheres, you're doing pascals, kilopascals, it's all the same. If this was atmospheres, we'd do atmospheres squared on top over atmospheres power of 4, and our overall would be atmospheres to the minus 2. Same as we were before. Now, if that doesn't sound very familiar, it's in terms of maths, when you divide, you subtract powers if the coefficient's the same. So it's the same as saying 2 minus 4, which equals minus 2, and put the atmospheres in front of it. Atmospheres to the minus 2. Okay, so KP. When we look at KPs, they can start spicing up the questions a little bit. So at equilibrium, they might tell you one of the products has this, and then they might say, oh, or at the start they have this, and this, that, this. This isn't as good an example for that, but it's the Harper process, and it's a common one. Okay, so in a question, they could say, find out the partial pressure of each one of these. Now, partial pressure is the pressure given off by each of these as a result of being in a container, and total pressure is all the partial pressures added together in that container. Now, when you're working out pressure coefficients, if you noticed, we actually used normal brackets instead of square brackets. That's because we're not doing concentrations. So in this case, we're going to be using partial pressures. And the way in which you can work out partial pressures, you can work out by doing molar and ratios. Yeah, so like that. So they could say, okay, the partial pressure, the total pressure of this whole unit is 200 atmospheres, will do. So 200 atmospheres, and we're told that at the start of the reaction we have 3 moles of this. Boom. And at equilibrium we have 5 moles of this. Okay? So we need to set up a little table. So I'm going to do it as start, change, or delta, as equilibrium, which I'm just going to write as EQ. Now for this we need to do N2, H2, and at this point here we have NH3. So we're told we have 3 moles of N2 to start off with. So we put in 3 here. Okay. Now this is a stoichiometry 1 to 3 ratio, so times that by 3. We get 9 moles of H2, and at the start of the reaction we have 0. Now, at equilibrium, we're told that this has molar ratio, has 5 moles. So the change in this is plus 5. So that means the change in this must be a multiple of 5. So the stoichiometry ratio between 2 and 3, we got times 5 by 1.5. So 5 times 1.5 is 7.5. So it's going to be plus 7.5. And this is going to be plus 5 over 2. Which is plus, oh sorry, minus, these are, getting ahead of myself here, minus 7.5 and minus 2.5. So at equilibrium we have 0.5 moles of that, we have 1.5 moles of that, and we have 5 moles of that. Congratulations. So now we need to work out the molar ratio. I think ratio is the right word, but I like the word ratio. So at equilibrium we have 5 moles of NH3. So 5 over 5 plus 1.5 plus 0.5 is equal to 5 over 7. So to find the partial pressure of this, we do ammonia at this. So let's say they told us the temperature. This was all at 500 degrees C. At 500 degrees C, there are 200 times 5 over 7 atmospheres of NH3. So 200 times 5 over 7, so it's going to be 1,000 over 7, which I can't do in my head, is 142.9 atmospheres. Okay. And now of this one we have 1.5 over 7, which is equal to 0.214. So 0.214 equals 42.9 atmospheres. And 0.5 over 7 is 1 over 14, or 0.07 times 200. And we get 100 over 7, or 14.3 atmospheres. Now these should add up to be total. I've rounded, so I'm not quite sure if it's going to go in nicely. It's close. If you add all them together, you get 200.1. Now that's probably just a rounding error, but that's proving that when we work out the moles, that all these must add to 1. So to find out the Kp of this reaction, we do use their partial pressures. So the Kp of this reaction is going to be 142.9 squared all over 14.3 times 42.9 cubed. I'm putting that into my calculator. I get a value of Kp to be 0.018. So this is showing me that there's a low product of NH3. Now that is actually true for the hard process. The hard process doesn't have a very good yield, so you'd have to pre-alter maybe some degree C, but this is probably about room temperature for that kind of poor yield. But this is when they could ask you a follow-up question. Oh, why did we do a 500 degrees C? This to increase rate maybe, and maybe it would increase yield, but I'm pretty sure it's exothermic. So increasing temperature would actually decrease in terms of Le Chatelier's principle. Because remember, temperature is also the only thing that can affect pressure. And the Kp constant. Concentration doesn't affect it, pressure doesn't affect it. So that's it. I hope that was helpful.